That's great. Thank you so much for allowing me to talk today. My name is George Weaver. I'm from Keele University in the UK. I'm a third-year PhD student at the minute, working on, as it says, using neural networks to estimate stellar ages from lithium equivalent widths. So just as a quick, brief overview of what we've been doing, the aim is to determine ages from photospheric lithium. This work's been focusing on the Eagles model of Jeffries et al. 2023 and improving that model with a machine learning fit to the data. And then, as mentioned before, constraining some of those issues that we see in terms of the dispersion of lithium in the photosphere. I'm going to skip over this very quickly because it's very much been explained. Our initial Eagles model, so from Jeffries et al. 2023, made use of the Gaia ESO spectroscopic survey. We've got high resolution spectroscopy for thousands of stars, so about 6,200 stars were used in the model. Crucially, in a set of star clusters that have got ages between 2 and around 8,000 megayears from the VLT in Chile. We have our initial model here, so this was our traditional analytical model. As it says, 52 Gaia ESO clusters, around 6,200 stars, fit with the traditional mathematical fitting method, 8 parameters, and then 5 also to describe the intrinsic dispersion in those equivalent width values. The important bit here at this point is that Jeffries decided to use equivalent widths rather than abundances, just to avoid a few of those issues from additional sort of model uncertainties when converting from observables into abundances directly. We have some of the initial results here, so we're getting up to around about 0.1 depth in precision in the most sensitive areas. So the initial model was indeed a success. And we can see a few of the fits to some coeval clusters here. We've got IC2602, 2391, the Pleiades, and M35. And those are our isochrones passing through. And the shaded region is our errors, our dispersion, sorry, at that best fit. But there were issues. As I'm sure you can imagine, we've got a pretty poor age fidelity above about a gig a year, and we'll go into more detail about those in a second. That doesn't appear to be related in any way to metallicity. We've obviously got a lot of other things that were mentioned in the previous talk that may well help with that, and that's what we're going to look at in a second. And then just at the bottom right there, some of the high metallicity clusters that we've looked at as well, we have poor fit to those where the isochrones are not willing to be flexible enough to properly fit that data. And this is reason one for our move into using a neural network. I think it's illegal for me to give a talk about machine learning without using one of those diagrams, so I apologize for that. But essentially, we're looking to apply more flexibility into that model than just a straight 8 parameter or 8 plus 5 parameter analytical fit. We've got our neural network here that takes into account age and effective temperature, and from that produces predictions of the equivalent width and the intrinsic dispersion in that equivalent width. As I say, the flexibility is a big part of this, and another part of it, which is more of our sort of next steps, as you'll see at the end, is that this is much more expansible, and that's why we've added that sort of etc there, that we can add in far more age indicators to hopefully constrain some of those problems we've mentioned. I'll skip over very quickly the basics of our neural networks, but just on this slide here, on the right-hand side there, we've got the dropout method. I'm sure you've heard this before, but if not, essentially during the training, some of a given fraction of the neurons within the neural network are switched off. That changes through each epoch of training, so that we produce essentially a lot of models that are all slightly different. That helps with our regularization and overfitting. There's also a part of our prediction process, as we'll see in a second. So to give a sort of quick overview of our results there, on the left-hand side, we've got the Eagles isochrones. So we've got equivalent width on the y-axis and effective temperature on the x-axis. And then on the right here, we've got our neural network. This neural network set of isochrones, we have 2,000 iterations of the model predictions, again, using that dropout method that I've just mentioned. And although superficially they're very similar, we do see 2 major differences in these. First off, we can see that additional flexibility. Those isochrones are much less constrained. Firstly, they don't have to monotonically decrease in equivalent width with age, which is something that was the case in Eagles. The first method of Eagles, we can also see those dips are rounded out. We don't have a set threshold at which that cutoff happens. We also see just at the top, you can sort of slightly see that that there are in fact some crossovers in those isochrones that we'll talk about very quickly for a second. So here we've got just our isochrones between about 1 and 10 megayears. And what we see, in fact, at this point is that from 1 to around about 6 megayears, we're actually increasing in equivalent width in the isochrones. So the average equivalent width of our data is increasing. And then at that point, lithium depletion starts. And that's our brown isochrone there, just starting to move into the lithium dip. I'll show that on a little quick video here of all of our isochrones. We've got the initial model in the black line and our new artificial neural network model in red. You see we increase at first. We have our dip, again, not quite as constrained, more flexible, moves slightly from left to right. We've got very similar isochrones, but that additional flexibility is giving us better fits for things. Just on the crossovers, the first thought is, well, are we just overfitting to the data? It is inherent in that data. We do see it there, but again, this is on the left-hand side and the right-hand side here, we've got the temperature bins, just the distribution of our training data, equivalent width and equivalent width and age on the Y and X axis respectively. It is there, but it's dominated by 2 clusters. The 2 largest on the far left, the very youngest is NGC 6530, and the sort of central large cluster is NGC 2264. So this is in the data, but it's pretty strongly correlated to just those 2. There are a few reasons why sort of astrophysically this may make sense. So we don't expect any depletion at these points. I don't think there are any evolutionary models that would allow for depletion at those young ages. But what we might expect is changes in equivalent width from different effects. So here we've got the lithium equivalent width curves of growth from Franceschini and the evolutionary tracks from Barat 2015. And we see that for a fixed abundance of lithium, we do in fact expect, as the star moves through the pre-main sequence phase, some increase in equivalent width of around the same magnitude due to pressure broadening. And in the same mode as that, we might also expect that accretion and veiling to drag down the average equivalent width that we're seeing at those very young ages before the disks dissipate. Very importantly, in our artificial neural network, not only are we slightly better fitting the isochrones themselves, we're also significantly more realistically fitting the dispersion. So this is log age on the y-axis against effective temperature. The red areas are areas where the eagle's initial estimation of dispersion is larger. The blue areas are where the artificial neural network is predicting a larger dispersion. In our young stars, we're almost entirely larger dispersion in the artificial neural network. This is much better fit to the data. We're adding in our aleatoric uncertainty as well with how the model works. And then in the oldest ages, we kind of have this little split between higher and lower in the neural network. This is a point where Eagles is not able to properly model this. Their dispersion model depends on the reduction in equivalent width, or the speed of the reduction in equivalent width. And I'll skip through to just our single star differences here. You can see there are areas where we don't get a prediction at all. What we'll get in those sort of white areas over there is a limit from both models. But you can see where our additional dispersion, I'll just show this one star, star A at the bottom left there. In the artificial neural network, our additional dispersion here is meaning that the flat prior in age for a single star is taken over, and we're getting just a limit for that star's age. Skip through to our cluster estimation. So again, in comparison, just the residuals in comparison with Eagles on the left and in comparison with the literature age on the right. Firstly, this is in fact giving us very similar results to Eagles. I want to point out 2 major things. One is that we are now able, with this new model, to give age discrimination at lower ages. So we're going down to 1 megayear in terms of producing peaks in the probability distribution. And the second is that we still have those issues above a gigayear. So our additional flexibility is not quite fixing all of the problems. We have some nice fits here. This is Gamma Velorum and Blanco 1 with both the neural network and Eagles fits. And then we have the pesky ones like M67. This additional flexibility, although it's given us improvements, is still not enough to be able to fit those awkward lithium equivalent width isochrones. Both of these clusters here, Hafner 10 and M67, are almost exactly the same literature age at about 3.5 gigayears. And yet we're seeing very different age predictions from the model. We've got our blue isochrone there predicted for Hafner 10, our red predicted for M67, and in between is the actual literature age, what the predicted isochrone should look like. Those low lithium objects for M67 dragging the isochrone down, and the opposite is true for Hafner 10 now. On our non-JES sample, so not the clusters that we've trained on, we're seeing, again, very good fits to the data. We're still getting reasonable fits, and we're still very, very close to the Eagles estimates. You might see those two ones at the top there, slightly above 8.5 in log age, and think, well, that's brilliant. Unfortunately, Hyades and Praesepe, they're still not fitting very well. So we're showing that we need some more in the model to make sure that we get what we need. So as a vague summary, Eagles has now got use of that ANN model, predictions for lithium equivalent width and dispersion. If you go to the QR code there, it should take you to the GitHub page of the version 2 model. Got a grid of results, which is the mean of those 2,000 predictions from the dropout method. We get a more realistic fit to dispersion and a likelihood determination down to a mega year now instead of 5. There are some issues still in those clusters above a few hundred mega years, and we're not fitting everything perfectly. But why bother using the neural network if it's just giving us some small improvements? Well, what we're doing as our next steps, at the minute, we've got a paper that's very close to submission. Again, if you can't wait that long, then the neural network model is now available on the GitHub there. We're testing further parameters that may impact lithium equivalent widths, such as our rotation periods and activity. And then we're looking at our expansion, which is our major reason for using the neural network. We're implementing new methods to sample larger parameter spaces, an MCMC sampler at the end of this, and then expanding the model into further age-dependent outputs, so things like activity and rotation. And then we'll be looking at expanding our training data with upcoming surveys. So a little mild confusogram there, but essentially this is the aim at the end, to have those inputs and be able to sample from a much larger set of age-dependent indicators. Thank you very much for listening. If you've got questions other than that, please do email. Yes, so Alex says, hi, George, very impressive work. Could you please comment on the turnover in lithium equivalent width for the early M dwarfs between 1 and 4 mega years? Is this due to some slight variation in TEF, hence differences in the curve of growth transformation? So I'll start off with that one, if I can go all the way back to my initial bit there. So this is something that we don't exactly know what's causing this. As I say, this is dominated very heavily by just those two clusters in the data. So should there be any discrepancy in the literature ages for those clusters, some difference in the order that's actually inherent that we've got wrong, that could very well explain it. But the major two that we've come up with that do seem to provide a reasonable astrophysical explanation for these are the evolutionary tracks where we are contracting and increasing pressure broadening in that PMS phase, and that's increasing the lithium equivalent width despite the abundance being fixed. And then, as I say, accretion disks, which we do seem to see in our training data. So the plot on the right here, we've got those accretors with an alpha W, Gaia alpha W greater than 2 in blue, and the rest of our stars in red. So there is a sort of reasonable explanation for that if it is inherent in the data. And then Alex has asked as well, also, if you have time, are the equivalent widths in lithium directly from the final JES IDR6 catalog? No, in answer to that, those lithium equivalent widths are from Jackson et al. 2022, I believe.